Hello my friends and welcome back to the You Can Do TV channel. A 150-ton iron hat enters the rolling stage, marking one of the most critical forming operations in heavy steel fabrication. This decisive process transforms thick plate into precise curved geometry under immense force, where dimensional accuracy directly determines structural integrity. Such components are essential for offshore wind and oil platform foundations, demanding strict tolerance control, material consistency, and defect-free forming to withstand extreme marine loads. This demonstration reveals the demanding manufacturing sequence required to produce a hot wound spring engineered for subsea oil and gas service, where reliability under extreme pressure is critical. A steel bar nearly 3 inches in diameter is heated to the austenitizing range, allowing controlled plastic deformation during hot coiling. The red-hot material is formed into a massive helix, approaching 5 feet in height, with a final weight near 1,000 pounds. Subsequent quenching and tempering cycles refine the microstructure, delivering the necessary strength, toughness, and fatigue resistance. Precision finishing and dimensional inspection ensure the spring performs reliably in corrosive offshore environments. Forged steel represents the intersection of tradition, metallurgy, and modern heavy manufacturing, and few companies embody that fusion more completely than Edelstahlwerke Rohstahl. The manufacturing chain begins with the strategic procurement and preparation of approximately 30,000 tons of raw material inventory, maintained in diverse block geometries and cross-sections. Primary material focus includes alloyed engineering steels, quenched and tempered grades, case-hardening steels, and corrosion and heat-resistant alloys. More than 100 standardized materials are available according to international specifications, while customer-specific chemistries are produced through coordinated metallurgical planning. Material preparation requires high-capacity sawing systems where circular and band saws process billets, pre-forged shafts, and blocks with millimeter precision. Components up to 1,800 millimeters in diameter, 15 meters in length, and 35 tons per piece are cut to calculated forging weights. After sectioning, billets are heated to temperatures ranging from 550 to 1,250 degrees Celsius before entering the forming stage. Forging operations combine traditional deformation principles with modern industrial power. Smaller components between 10 and 2,500 kilograms are shaped using steam hammers and hydraulic presses, while larger workpieces are manipulated under heavy hammers, with electro-hydraulic manipulators capable of handling extreme loads. For massive forgings up to 45 tons, 4-column hydraulic presses deliver forces reaching 40 meganewtons, producing axles and drive shafts with exceptional dimensional accuracy in single forming sequences. Integrated electronic controls assist press operators in maintaining deformation precision and repeatability. Seamless rolled rings represent another core manufacturing capability. Pre-forged pierced discs are transferred to advanced radial axial ring rolling mills, where computer-monitored processes control wall thickness, diameter growth, and structural consolidation. Rolling forces up to 250 tons per axis enable production of rings up to 3,500 millimeters in diameter and 8 tons in weight, used later in gears, bearings, flanges, and sealing systems. Thermal processing plays a decisive role in achieving final mechanical performance. 33 heat treatment furnaces equipped with modern burner technology perform quenching, tempering, annealing, normalizing, stress relieving, and solution heat treatments at temperatures reaching 1,250 degrees Celsius. Controlled thermal cycles optimize hardness, toughness, machinability, and fatigue resistance while maintaining energy efficiency through integrated process flows. Mechanical finishing operations occupy approximately 9,000 square meters of machining space, staffed by over 130 specialists. CNC turning, milling, deep hole drilling, and large diameter carousel machining enable production of complex geometries with tight tolerances. Specialized equipment supports components up to 15 meters long or 35 tons in weight. Quality assurance is embedded throughout manufacturing. Certified to ISO 9001 standards, inspection protocols include automated ultrasonic testing, spectrometric chemical analysis, tensile and impact testing, dimensional verification, and hardness measurement. Traceability is maintained through stamped identification numbers assigned to every component. Logistics efficiency is supported by a 21-meter-high automated storage system with nearly 3,000 pallet positions, integrated with dedicated transport fleets to ensure responsive delivery schedules. The resulting forged products serve demanding sectors including wind energy, marine propulsion, heavy machinery, mining, steel production, and power generation, applications where reliability is not optional but essential. The spring manufacturing process at Cars Chile, a company belonging to the Indumatora Group, reflects decades of metallurgical expertise and industrial specialization. Production begins with high alloy steel selection, typically say 615OH, composed of carbon, manganese, chromium, silicon, and vanadium. This composition provides excellent elasticity, strength, and toughness while controlling grain growth at high temperatures, making it ideal for heavy-duty compression and traction springs used in mining and rail applications. The manufacturing sequence starts by cutting steel bars to the required length and diameter. The bars are straightened and surface ground to eliminate defects such as decarburization or microcracks that could lead to failure during heat treatment. The ends are then heated to approximately 900 degrees C and hot rolled using elliptical rollers to form the spring seats. Next comes controlled heating to achieve austenitization, followed by coiling in precision dies that ensure consistent geometry. While still red hot, the spring undergoes oil quenching to transform the microstructure into martensite, producing maximum hardness. Because the quenched material is extremely brittle, tempering is performed at roughly 390 to 460 degrees C for at least 1 hour in a controlled atmosphere furnace to restore toughness and relieve internal stresses. Subsequent operations include grinding the seating faces flat, shot peening with high-velocity steel spheres to significantly increase fatigue life, and mechanical testing under compression to verify load capacity and elastic recovery. Finally, an electrostatic coating protects against corrosion, particularly in aggressive environments such as mining operations and coastal climates. Through advanced metallurgy, rigorous testing, and accumulated technical knowledge, Cars Chile delivers durable, high-reliability springs trusted by major mining and railway companies throughout the region. Precision fasteners may appear simple, yet their performance determines the safety of massive structures and heavy machinery operating under extreme loads. High-quality bolt production follows a tightly controlled, fully automated manufacturing sequence, including acid pickling, material preparation, cold forging, thread rolling, and continuous heat treatment to achieve precise mechanical properties and dimensional accuracy. Nut products are manufactured through hot forging, shot blasting, and continuous thermal processing. Every stage is reinforced by a rigorous quality assurance system, from incoming material inspection to in-process verification and final testing using advanced measurement equipment. The finished components are widely applied in bridges, structural construction, heavy equipment track systems, and industrial assemblies. Advanced thermal processes, annealing, normalizing, quenching, and tempering, enhance durability and fatigue resistance, while integrated automation and logistics management ensure consistent production efficiency and global reliability. Extruder feed screw manufacturing, rebuilding, and design are essential for maintaining efficient plastic and polymer processing operations. A precisely engineered feed screw ensures uniform material conveying, controlled melting, and stable output quality. Modern manufacturing relies on advanced CNC machining, precision grinding, and specialized heat treatment to achieve tight tolerances, smooth surface finishes, and superior wear resistance. Rebuilding services restore worn or damaged screws to original or upgraded specifications. Typical procedures include hard facing, chrome plating, nitriding, or applying bimetallic coatings to improve durability and corrosion resistance. This cost-effective solution extends equipment lifespan while minimizing downtime and replacement expenses. Custom screw design considers resin type, temperature profile, pressure demands, and production throughput. By optimizing flight depth, compression ratio, and mixing sections, engineers enhance processing efficiency, material homogeneity, and overall extrusion performance. Altec Metal achieves a national milestone with the casting of 7,021 aluminum slabs using more than 80% industrial scrap content. The process integrates advanced melt preparation, impurity control, and precision continuous casting to ensure chemical homogeneity and structural integrity. This high recycled input significantly reduces energy consumption and carbon impact while maintaining the mechanical performance required for demanding industrial applications. Advanced metallurgical control and automated processing define the production approach at Deal Brass Solutions. Manufacturing begins with carefully selected primary and secondary raw materials, including recycled metals integrated through a closed-loop system. Precision melting and alloying technologies ensure exact chemical composition across more than 75 brass grades, including lead-free formulations engineered for potable water compliance. Fully automated casting, extrusion, and forming lines maintain dimensional tolerances and repeatability, supported by real-time process monitoring and quality analytics. Downstream machining compatibility is optimized through controlled microstructures and surface integrity. Certified management systems govern every stage, ensuring metallurgical consistency, mechanical performance, and reliability for demanding industrial infrastructure and mobility applications. Continuous R&D refines alloy properties for future engineering requirements. Precision, heat, and force converge inside the rolling mill at United Steel Industries LLC, where semi-finished steel is transformed into high-performance structural products. Reheated billets exit the furnace at controlled temperatures to ensure optimal plasticity before entering a sequence of roughing and finishing stands. Each pass progressively reduces cross-section while refining grain structure, improving strength and toughness. Automated guides, synchronized roll speeds, and real-time dimensional sensors maintain tight tolerances throughout deformation. Thermomechanical processing parameters are continuously monitored to achieve uniform mechanical properties along the length. Downstream cooling beds regulate microstructure evolution, while inline inspection systems verify surface quality and geometry, ensuring the final steel sections meet rigorous construction and industrial standards. At U.S. Bolt Manufacturing, bolt production follows a tightly controlled engineering workflow where metallurgy and precision machining define performance. The process begins with high-grade steel selection, followed by cutting and cold or hot forming to create the bolt head and basic geometry. Thread rolling then compresses the material to increase strength while achieving accurate tolerances. Heat treatment cycles, quenching and tempering, enhance hardness, tensile capacity, and fatigue resistance. Surface finishing, including coating or galvanization, provides corrosion protection for harsh environments. Dimensional inspections, mechanical testing, and quality verification complete the sequence, ensuring every fastener meets strict structural standards for construction applications. A motorcycle wheel rim must perform under relentless mechanical stress, absorbing impacts, supporting vehicle weight, and maintaining precise alignment at high rotational speeds. Inside a specialized factory, manufacturers such as Yamaha Motor Company and Honda Motor Company rely on advanced production systems where materials, science, forming technology, and precision machining converge to deliver safety-critical components. Production typically starts with aluminum alloy, selected for its optimal balance between strength, weight, and corrosion resistance. For cast rims, alloy is melted in temperature-controlled furnaces and poured into molds using gravity or low-pressure casting methods. Advanced processes such as flow forming may follow, where rollers compress and elongate the rim section, refining grain structure and increasing fatigue strength. Forged rims take a different route. Solid billets are pressed under extreme force, aligning the metal's internal grain to create superior structural integrity with reduced material thickness. Once the primary shape is formed, CNC machining defines the critical geometry. Mounting faces for brake discs, hub interfaces, and bearing seats are cut to tight tolerances to ensure rotational accuracy and proper load distribution. Next is the surface finishing technology, glossy, which helps resist corrosion and ensures aesthetics by dipping into a liquid. For spoked rims, rolled sections are welded into circular form before precision drilling establishes spoke hole angles that optimize force transfer between hub and rim. Final inspection integrates dimensional measurement, testing for internal defects, and dynamic balancing verification. From traditional wire spoke designs to modern forged and composite variants, rim manufacturing reflects engineering precision that directly influences handling stability, braking efficiency, and long-term durability. The manufacturing of a four-cylinder automobile engine block begins with metallurgical precision, where raw aluminum ingots are transformed into a high-performance structural component. The first stage involves smelting, during which aluminum is heated in controlled furnaces to reach a molten state. Careful temperature regulation ensures uniform composition while removing impurities that could weaken the final casting. Next comes refinement. The molten aluminum undergoes degassing and filtration to eliminate trapped gases and inclusions, producing a cleaner, more consistent liquid metal with improved mechanical properties. Alloying elements may also be introduced at this stage to enhance strength, thermal conductivity, and wear resistance, critical factors for engine durability. The refined aluminum is then transferred into high-pressure die casting systems. Molten metal is injected into precision steel molds at controlled speed and pressure, forming the complex geometry of the engine block, including coolant passages and cylinder structures. Rapid solidification improves dimensional accuracy and structural integrity. After casting, the block proceeds to cooling, trimming, and subsequent machining processes that define final tolerances and functional surfaces essential for engine performance and reliability. Geothermal energy manufacturing demands multidisciplinary precision, and Ormat Technologies has built an integrated production ecosystem capable of delivering complete power plant solutions, from subsurface resource utilization to fully operational generation systems. With more than 180 power plants deployed across over 33 countries and approximately 3,000 megawatts of installed capacity, the company's manufacturing philosophy centers on vertical integration, engineering control, and lifecycle reliability. Production begins within a large-scale machining environment where advanced CNC equipment transforms raw materials into critical geothermal components under tightly controlled tolerances. A central element is the geothermal production pump, engineered, manufactured, and performance-tested in-house to withstand high-temperature brine environments and continuous duty operating conditions. From the pump, geothermal fluid is routed through a piping network into the heat exchanger system, where thermal energy transfers to an organic working fluid within vaporizer, preheater, and recuperator units. Heat exchanger manufacturing involves heavy plate fabrication, automated submerged arc welding systems capable of tens of kilometers of weld seams annually, and extensive manual welding operations supported by non-destructive testing protocols. Tube bundle assemblies incorporate large quantities of precision-aligned small-diameter tubes supported by baffles and tube sheets before integration with the outer pressure shell. Final assemblies undergo hydrostatic pressure testing to validate structural integrity prior to coating and certification. Turbine manufacturing follows with large structural components, including turbine housings, outlet cones, and bases, produced through machining and thermal stress relief treatments. Rotating assemblies such as shafts, wheels, and blades are manufactured with high dimensional accuracy and dynamically balanced throughout staged assembly. Installation of bearings, seals, nozzle rings, and lubrication systems occurs in dedicated mechanical assembly areas, followed by extended operational testing to confirm performance stability under load conditions. Air-cooled condenser production adds another layer of complexity, combining finned aluminum tubing, robotic header welding, structural frame fabrication, and ASME-compliant pressure testing. Electrical control systems are assembled separately within automated logistics-supported facilities, where precision wiring and cabinet integration enable seamless plant automation and monitoring. A defining characteristic of the manufacturing strategy is modularity. Equipment is designed for simplified transportation, rapid site installation, and maintainability across diverse geographic environments. Continuous research and development activities support performance optimization, while reinjection systems maintain geothermal reservoir sustainability. The result is a fully engineered geothermal power solution, in which mechanical, thermal, and electrical subsystems operate as a unified energy conversion platform, demonstrating how advanced manufacturing directly enables reliable, renewable power generation at industrial scale. A shovel is engineered through a disciplined sequence where metallurgy meets precision forming. Thick steel plates, each sheet yielding up to 24 blanks, are first cut to size, with material thickness selected according to product class. Mechanical edging follows, creating a sharp lip that improves soil penetration and digging efficiency. The prepared blanks then travel through an automated forming line where the scoop geometry emerges and the brand stamp is pressed into the steel. Heat treatment defines performance. The scoop is heated to high temperature and rapidly quenched using a proprietary cooling method to achieve hardness. Tempering at controlled lower temperatures restores toughness and elasticity, preventing brittleness. Final inspections verify hardness, surface integrity, and the absence of cracks, ensuring each shovel delivers durability, resilience, and reliable field performance. A surge of torque, rising temperature zones, and precisely metered ingredients. This is where raw material begins its transformation into a controlled, engineered product. The Buehler Group extruder operates as a synchronized system in which mechanical force, thermal energy, and automation work in continuous balance. The process opens with the assembly of modular screw elements, each configuration carefully selected to determine shear intensity, pressure development, and residence time inside the barrel. During startup, Heaters bring each zone to its target temperature, while drive systems gradually increase rotational speed, allowing material to enter without shock loading. Once production stabilizes, integrated sensors track torque, pressure, and throughput in real time, enabling automatic adjustments that maintain consistent product structure and quality. Operational safety is engineered into every phase. An emergency stop immediately depressurizes the system and halts motion, preventing mechanical damage or operator risk. Maintenance efficiency becomes evident through the automatic screw push-out function, which extracts internal components quickly for cleaning or inspection. When production requirements shift, recipe changes recalibrate feed rates, screw speed, and thermal profiles with minimal interruption. The shutdown sequence completes the cycle through controlled cooling and pressure release, preserving equipment integrity while preparing the system for the next operation. Industrial precision comes to life inside the manufacturing facilities of Brightspan, where thousands of structural components are engineered, fabricated, and verified with uncompromising accuracy. Every small part begins its journey with a dedicated production order, supported by detailed engineering drawings tailored to exact customer requirements. From the earliest fabrication stages, welders and technicians maintain continuous dimensional verification, ensuring each component conforms precisely to blueprint specifications before progressing to the next operation. Advanced equipment forms the backbone of this production ecosystem. CNC-controlled tube bending machines shape web members with remarkable repeatability, processing long sections of steel tubing within seconds while maintaining tight tolerances essential for structural alignment. End preparation systems clip and finish tube edges to create optimal weld joints, while industrial cold saws cut pipe sections up to several meters in length with clean, accurate edges. Drill presses, supported by precision templates, guarantee consistent hole placement across high-volume production runs, reinforcing assembly accuracy during later construction stages. As components advance into welding operations, fabrication scales dramatically. Large truss assemblies take shape inside dedicated welding cells, where synchronized teams coordinate tack welding and final structural joining. Overhead cranes maneuver heavy sub-assemblies into position, allowing welders to maintain optimal welding positions while ensuring operator safety. Structural spans reaching hundreds of feet demand absolute dimensional control, and post-weld verification confirms that every assembly will integrate seamlessly at the installation site. Rolling and forming technologies introduce another layer of precision. Numerically controlled rollers shape pipes into exact radii required for curved structural members, with programmable settings enabling repeatable production across multiple projects. Quality control tables, adjustable for different geometries, allow technicians to confirm conformity quickly before components move forward. Incoming materials, whether sourced externally or fabricated internally, undergo receiving inspections aligned with strict process control plans to verify dimensions, material grades, and order quantities. Automation further elevates manufacturing consistency. Robotic welding systems position components within fixtures, execute tack welds, and complete full weld passes with repeatable precision. Following robotic operations, skilled technicians inspect weld penetration and geometry to confirm compliance with structural requirements. CNC plasma punch tables cut and perforate steel plates with programmable accuracy, while bandsaws process hollow structural sections used in major building frameworks. Each first article component is validated before batch production proceeds, eliminating variability and ensuring uniform quality. Secondary processing operations refine components for final integration. Swagging systems reduce pipe diameters to enable telescoping connections, while hydraulic presses flatten and punch purlin ends for structural support applications. CNC profile cutting machines produce foundation rails and web members with complex geometries, maintaining alignment accuracy critical to large-span building systems. Cleaning equipment removes mill-scale burrs and slag, preparing parts for inspection and assembly without contamination risks. One of the most critical quality stages occurs after fabrication: corrosion protection. Completed trusses undergo hot dip galvanizing, immersing entire assemblies in molten zinc to achieve full internal and external coating coverage. This method eliminates the corrosion vulnerabilities associated with welding pre-galvanized materials, significantly extending structural lifespan. After galvanizing, components return for comprehensive inspection, where technicians verify hole alignment, mating surfaces, and coating integrity to guarantee efficient field assembly. Final preparation transforms finished structures into transport-ready systems. Components are bundled, bolted, and spaced with protective materials to prevent damage during shipping. Certification labeling confirms that each piece has undergone full inspection and approval prior to dispatch. Through the integration of advanced machinery, robotic automation, rigorous inspection protocols, and controlled finishing processes, the manufacturing operation delivers structural components engineered for durability, precision fit, and long-term performance in demanding construction environments. Industrial-scale steel fabrication requires uncompromising precision, and Stalcon operates with advanced production infrastructure and heavy-duty engineering capability to meet that demand. A 500 square meters workshop integrates specialized cranes, high-capacity transport systems, and dedicated final assembly zones designed for extremely large structures, including ship loaders weighing up to 1,000 tons. Dual painting and blasting chambers provide controlled surface preparation and coating processes, ensuring long-term corrosion resistance in aggressive operating environments. Manufacturing output covers bar and frame overhead cranes, pipe cranes, dividers, transporters, stacker reclaimers, harbor handling systems, and bulk material loaders and unloaders. Process industry equipment includes tanks, silos, pipelines, boilers, industrial furnaces, and complete waste gas treatment installations for power plants and cement facilities, incorporating filtration systems, ducts, and exhaust stacks. Infrastructure fabrication extends to gangways, bridges, overbridges, industrial halls, commercial pavilions, framework buildings, and sports structures. Marine sector capability includes vessel sections, onboard equipment, and heavy-duty ferry ramps. Productivity is achieved through optimized workflow sequencing, precision machining, and strict dimensional control, delivering consistent performance across complex assemblies. Technical specialists also support no-load commissioning phases, verifying operational readiness and mechanical integrity prior to deployment across industrial, maritime, and infrastructure applications. The 30-megawatt CD4 geothermal project, part of the Mammoth Complex in California, has officially entered commercial operation, marking a significant milestone in advanced renewable energy deployment. Binary cycle technology transfers geothermal heat to a secondary working fluid with a lower boiling point, enabling efficient turbine operation while maintaining a closed-loop system that minimizes environmental impact. Construction of the CD4 facility required extensive subsurface and surface engineering coordination. The development phase included geothermal resource confirmation drilling, reservoir modeling, and production well installation to ensure sustainable steam and brine supply. Reinforced concrete turbine foundations, prefabricated steel structures, and modular process skids were assembled in parallel to accelerate the construction schedule. Air-cooled condensers, critical for water conservation in the region, were erected using heavy lift cranes and precision alignment procedures to maintain thermal efficiency. High-pressure piping systems connecting production wells, heat exchangers, and reinjection wells were fabricated with corrosion-resistant alloys to withstand geothermal fluids containing dissolved minerals. Electrical integration involved step-up transformers, switchgear systems, and grid interconnection infrastructure designed to meet California reliability standards. Commissioning activities included turbine synchronization, thermal performance testing, and automated control system calibration to optimize plant output across varying geothermal resource conditions. As part of the broader Mammoth geothermal network, CD4 strengthens regional renewable capacity while demonstrating the viability of next-generation binary geothermal technology. The project provides dispatchable clean energy that complements intermittent renewables such as wind and solar, reinforcing grid stability and advancing long-term decarbonization goals across the western United States. With a total capacity of 30 megawatts, the project expands Ormat's geothermal portfolio and contributes new renewable generation to California's grid under long-term power purchase agreements with multiple energy providers. The facility is also notable as one of the first geothermal plants constructed within the California ISO Balancing Authority area in decades, reinforcing geothermal energy's role as a dependable complement to intermittent renewable sources, such as wind and solar. Beyond electricity production, the CD4 project highlights the broader engineering advantages of modular geothermal plant architecture. Major components, including heat exchangers, turbines, pumps, and control systems, are manufactured, tested, and assembled with high precision before installation, reducing construction risk and accelerating commissioning timelines. The result is a power plant capable of delivering long-term operational stability, predictable output, and minimal environmental footprint. Steel arrives as raw potential, but inside Corpus Christi trailers, it evolves into purpose-built transport equipment engineered for endurance and performance. The fabrication process integrates precision cutting, structural welding, and heavy-duty forming to create a wide spectrum of solutions: truck bodies, dry vans, tankers, liquid storage units, livestock trailers, and specialized cowboy configurations tailored to demanding field conditions. Each project begins with structural design calibrated to load distribution, road stress, and operational environment. Frames are reinforced with high-strength steel members, ensuring torsional rigidity while maintaining optimal weight efficiency. Skilled welders execute continuous seams that enhance durability and leak resistance, particularly critical for tanks and fluid transport systems. Surface preparation and coating systems provide corrosion protection, extending service life in harsh climates and high-moisture environments. Customization defines the manufacturing philosophy. Dimensions, compartment layouts, suspension interfaces, and mounting systems are adapted to client specifications, whether for agricultural hauling, industrial logistics, or commercial freight. Quality control inspections verify alignment, weld integrity, and dimensional accuracy before final assembly. The result is more than a trailer or truck body. It is a mobile infrastructure asset designed to withstand vibration, impact, and heavy payload cycles. Through disciplined engineering and craftsmanship, Corpus Christi Trailers delivers transport solutions built for reliability, productivity, and long-term operational value. Water infrastructure depends on one principle above all: absolute reliability under pressure. At Northwest Pipe Company, engineered steel water pipe is manufactured through a highly controlled spiral weld process designed for strength, longevity, and leak-free performance. Steel coils enter the spiral mill, where drive rolls flatten the material and trim edges to precise dimensions before the strip is formed into a cylindrical shape. Continuous welding along the spiral seam, inside and outside, creates structural integrity across diameters ranging from 12 to 156 inches. Quality assurance is embedded throughout production. Non-destructive testing methods verify weld consistency, while hydrostatic pressure testing confirms each pipe section is completely sealed before shipment. Protective lining systems extend operational life. Cement mortar linings are centrifugally applied to produce a dense alkaline interior that reduces corrosion, while polyurethane coatings provide a durable moisture barrier for higher flow velocities. Exterior coatings, applied after abrasive blasting and surface preparation, protect against environmental exposure. Custom fittings, fabricated by certified welders, complete project requirements with the same inspection standards. The result is a pipeline system engineered for decades of dependable water transmission with minimal maintenance. Inside the production halls, powder tanker trailers emerge through a synchronized chain of precision engineering. Steel plates are cut, formed, and assembled into structural shells before advanced welding systems fuse each joint with consistent strength. Surface finishing and polishing refine the exterior, preparing it for protective coatings. The result is a transport vessel engineered for durability, safety, and long-term industrial performance. Electropolishing transforms metal at a microscopic level, dissolving peaks while leaving valleys intact, to create an ultra-smooth, mirror-like finish. Beyond aesthetics, the process removes embedded contaminants, enhances corrosion resistance, and reduces friction, making components easier to clean and longer lasting. Properly controlled parameters can also achieve passivation, forming a protective oxide layer without mechanical abrasion. Industries from medical devices and pharmaceuticals to aerospace and food processing rely on electropolishing for precision parts, tubing, and complex geometries. By refining surface topography rather than coating it, electropolishing elevates performance, hygiene, and reliability, turning ordinary metal into a high-integrity engineering surface for demanding applications today. Automated welding technology plays a decisive role in the production of pressure vessels and transport tanks, where structural integrity and repeatable quality are non-negotiable. Robotic systems developed by Robotics demonstrate how advanced automation enhances both productivity and weld consistency during tank trailer fabrication. The manufacturing sequence typically starts with precision-formed shell sections and longitudinal seams prepared for automated joining. Robotic welding cells equipped with multi-axis manipulators and synchronized positioners ensure optimal torch orientation throughout circumferential and longitudinal weld paths. This coordinated motion control maintains uniform penetration, bead geometry, and heat input, minimizing distortion across large cylindrical assemblies. Integrated seam tracking sensors continuously monitor joint alignment, allowing real-time adjustments that compensate for tolerances in formed components. Programmable welding parameters, current, voltage, travel speed, and wire feed, are optimized for different material thicknesses and alloy compositions commonly used in tanker construction, including high-strength steels and aluminum alloys. Beyond structural welds, robotic systems also perform nozzle attachments, reinforcement rings, and mounting brackets, reducing manual intervention and improving workplace safety. The result is a highly repeatable manufacturing workflow capable of producing durable, lightweight tank trailers with superior fatigue resistance, demonstrating how robotic welding technology transforms heavy fabrication into a precise, data-driven industrial process. Advanced digitalization is redefining heavy equipment production, and Sany Renewable Energy demonstrates this transformation through intelligent manufacturing for the wind power industry. At its Beijing base, a 5 grams fully connected smart factory integrates automation, data systems, and flexible production to achieve higher efficiency, lower costs, and improved safety across multiple turbine platforms from 2MW to 8MW classes. Key assembly processes incorporate unmanned operation islands, where robotics and heavy-duty AGVs handle large component logistics, enabling automated material distribution throughout the production line via coordinated warehouse, AGV, and RGV systems. Flexible hub assembly lines support simultaneous multi-model manufacturing while maintaining industry-leading throughput during peak production cycles. Blade manufacturing advances include mobile robotic grinding units guided by laser positioning, delivering consistent surface quality while improving workplace conditions. Automated painting and stud installation further enhance repeatability. A plant-wide digital twin platform integrates R&D, production data and management systems, enabling real-time monitoring, predictive optimization, and precise lifecycle control across the entire smart manufacturing ecosystem.